Thank you. So I would like to thank the organizers for letting me talk. So I would like to present you some work that I recently did, especially in collaboration with my student Jean Claise, with David Antoine and Federico Piazza. And it's about an effective approach to dark energy and modified gravity, which in principle unifies most of the simple field dark energy unified gravity models that you know in the literature, and makes a sort of a spectroscopy of these models in terms of essential operators. I hope that the two join me not call me tonight and complain that they use So let me start with some motivations. We all know that data are compatible with the cosmological constant, but we have theoretical motivations to go beyond these features. And we also know that alternatives to GR will require a new degree of freedom. And as you know, the interactivity of theorists has been very active during the recent years. And there have been a lot of dark energy modified gravity models that have been proposed in the literature, all coming with different theoretical motivations and different observational consequences. So starting from GR, we have started to explore a large, big map of territory, looking for the treasure, so for the explanation of the different acceleration. And we have tried to generalize, to go beyond the GR by adding, for instance, a scalar field, or by extending the four-dimensional space-time, by breaking Lorentz variance, or adding a mass to the gravity. Okay. So, from the observational point of view, we know that all these new dynamics, these new degrees of freedom, will provide deviations from GR, time and space dependent deviations. And as David explained this morning, on small scales, these deviations are very tightly constrained by solar system tests. So we expect that most of these models are screened to pass this test. However, the cosmological large scales do still represent a window of potential discovery for modifications of gravity. And we know that given a background evolution, so for instance, given the Hubble time as a function of time, and given the matter content of the universe, the growth of structure is completely determined in GR. However, when we modify gravity, we expect that there are time and scale-dependent modifications for the growth of structures. And my claim is that we can look for new physics exactly on these large scales. And as you all know, what is nice is that in the future there will be a lot of surveys that will improve our current measurements and our current constraints by 1 or 2 orders of magnitude. If at some point we want to make into contact all these models that we currently have with observations, I would like to propose a sort of democratic approach, okay, to models, irrespective of their theoretical motivations, which is at the same time unifying, so it contains a larger class of these models and is effective in the sense that it doesn't care about the original motivations. So I will take an effective theory point of view, and I will try to describe all these models by avoiding redundancies, which appear when you make field definitions, for instance, and try to derive minimal action in terms of the minimal set of operators. So my point of view is that theories that share the same degrees of freedom, the same interactions, and the same regime of validity are completely the same. Okay? And in this talk, I will restrict these 3 things to the following assumptions that we can generalize. So I will assume that we have only one scalar degrees of freedom beyond the tensor degrees of freedom. That vector is all coupled to a metric, which we can call the metric. And then that we can describe the linear regimes, the linear regime for perturbation. Okay. Of course, all these are assumptions. They are not particular symmetries of what I'm doing, but so you can go beyond these assumptions. But in this talk, I will restrict to these three assumptions. Okay, let me start by constructing what will be my action for cosmological perturbations beyond GR. And the idea is that the scalar field, okay, which is present in the gravitational sector, breaks diffeomorphism, time diffeomorphism invariance, and there will be so in principle you can choose a time to coincide exactly with the scalar field, with the surfaces where the scalar field is uniform. And I will describe my space-time by using an ADM metric with a 3+1 decomposition, where the time coincides exactly with the scalar field at the surface. Now, in principle, spatial diffeomorphisms are still preserved on this preferential hypersurface. I'm just breaking time diffeomorphisms. So my action will be made by all possible terms that are invariant under spatial diffeomorphisms. Okay. So in principle, we can put in our action functions of time, for instance. Then the lapse, we know that it is invariant under spatial diffeomorphisms. And as you have seen, we are choosing a gauge, which is called a unitary gauge, where the scalar field has been eaten by the metric, so it has scalar field fluctuations have disappeared, and somehow the kinetic term is included in this lapse. Okay? And it can reappear once we reintroduce again scalar field. Another element, geometrical element, which is invariant under spatial diffeomorphisms is the extrinsic curvature, or the extrinsic curvature tensor, which, if you want, represents the way the spatial metric changes in time. So it's a sort of a time kinetic term for the metric. Okay. And then we have the Tri-Ricci scalar, or Tri-Ricci tensor, which is a sort of a spatial kinetic energy for the metric. Then you can add derivatives of these elements, or any contraction of these geometrical elements, and you can build up an action by adding all possible terms and operators that are invariant under this field. And then we would like to describe linear perturbations. So at some point we want to expand this action, but before doing that, let me show you that most of the theories that we know are already made up by these elements. Okay. For instance, you know that you can write a Lagrangian for GR in this way, because you can use the Gauss-Pedazzi relation to write the 4-Ricci scalar in terms of the product of the essential curvature and the 3-Ricci scalar. Okay. So this is sort of a kinetic energy for the graviton, and this is the potential energy. So I can add a scalar field. This describes what is usually called minimum quintessence. And in unitary gauge, the scalar field appears in this way. You have 1 over the lapse squared. And why? Because the kinetic term of the scalar field is just G00 in unitary gauge. So there is one, this is equivalent to 1 over n squared. And the potential is a function of time. Okay. Also, f of r, which is one of the most common models for modified gravity, can be written in terms of these elements. Here you have GR, but the mass Planck now depends on time by the function. And then there is a new term that does not appear here, which contains both the sensitive curvature and the lapse. So this contains both the time kinetic energy of the scalar field and the time kinetic energy of the metric. So it's a mixing between the metric and the scalar field, and this mixing is usually called rate, sometimes called rate. Okay. So let's go back. You see that most of the models are already written somehow in these basic elements. I want to consider the expansion of the most possible general action. So I will expand this action, okay, at second order, and then I will use the equations of motion inside for the background inside this action. So I derive the equations of motion, I plug them in, okay, and as a final thing, I remove higher derivatives at linear order second order interaction in order to avoid the possible presence of addition and decay of freedom, okay, which will be given by orthographic. Okay. So finally, what I get is the following action. Okay. So this, in principle, is the most general second order action without higher spatial and time derivatives, which describes all possible modifications from GR under these assumptions. So it contains GR. This is the GR expanded at second order, basically, okay, in absence of time dependence of this mass term, which simply becomes the Planck mass. This happens by setting all these operators to 0 and by taking this to be time instead. Now, all these operators, all these parameters in front of these operators, alpha k, alpha b, alpha t, alpha h, and alpha n that you can derive from taking the time derivative with respect to this mass, represent parameterized, so these are free functions that parameterize deviation or possible deviation from GR. Okay. And I'm using here a notation from this nice paper of Vernizzi and Sawicki. And notice that these parameters are completely independent from the background. So you assume that there is a background evolution given by the Hubble rate as a function of time. And then you can add this parameter without affecting the background. Okay, so there is a clear separation between background evolution, and linear perturbations. So now I'm going to show you that all these parameters contain most of the models that you know. Okay. So let's start by taking GR. So here this mass squared is a constant, and adding the first of these operators. So this contains the lapse squared. You remember that the lapse is the time kinetic energy of the scalar field. Okay, so this describes in fact all Ks and second quintessence models, typically Lagrangian, which are a function of the time and of the kinetic Okay, this just describes in the most general way all perturbations of this. Let's add another operator. And this is parameterized by alpha b. B is for private if you want. And this parameterizes linear perturbations in models where these sort of operators appear. So you have a k of x times a box phi. And it appears, for instance, in the decoupling limit of the GP, in Galilean models, or in the so-called K-Galileo-like energy. So now we are going to make this mass to be time dependent, and this way I can include also Van decay theory, things like that. And well, this action will include also perturbation of f of r and f of g and other models. And finally, you expect that this new parameter, you see, will change the spatial kinetic energy of gravitons. Which is sort of fixed in GR to the relation between what is here and what is here. And therefore you expect that it's going to change the tensor sound speed. And by adding this operator, you basically cover all possible or density theories, okay, at linear order. So our density theories are the most general Lorentz invariant scalar tensor theories with second order equations of motion. So in principle, you cover a large class of models that are scalar tensor theory models that are currently studied. And notice that in order to describe our density theories, you need 1, 2, 3, 4 equations of psi and x of the kinetic term. And instead here you're using only 5 equations of time, well, plus h if you want this 6 equations of time. So it's a great gain with respect to having so many equations of time and another one. Okay, here we are left with another operator. And in fact, we discovered that you can have other theories which linearize lead you to second order equations of motion. However, you can extend this theory to a nonlinear Lagrange, which once you derive the equations of motion, these are higher order, but you can combine this equation of motion in such a way that the fundamental degrees of freedom, the scalar and the tensor degrees of freedom, are only second order. Okay? So these theories do not contain new degrees of freedom according to Post-Rogowski instability. So we managed to explore a new territory by using this effective theory approach. So new theories that were not taken into account before have been uncovered by using this approach. So if I go back to my map of the pressure, now there are a series of theories that are completely described at the linear level, of course, by this approach. These are all these theories where there is a scalar degree of freedom. Of course, there is a new territory explored. You can, in principle, also describe with the same approach Lorentz evaluating theories like the Gauss condensate or Lava-Lipschitz. The scalar mode of different theories, this one or the decoupling limit of massive gravity, and also the four-dimensional reduction of these theories like Lipschitz, for instance. Okay. So just to make a short summary, by starting with this action, this action is completely given by symmetries by the fact that we are expanding around the Freeman-Robertson-Walker universe. There are no redundancies in the sense that these are the minimal set of operators that you can use to describe deviation from GR. And it allowed us to explore new theories. And now I'm going to show you that it's very easy to check theoretical consistencies of models by starting from this action, and also to make a robust prediction in terms of this parameter. So I will try to show you that this is the most efficient way to parameterize dark energy and modify gravity models on linear scales, okay, when you want to compare to observations. So you know that if you have a field, you would like to avoid that its time kinetic energy is negative. So you would like to avoid that it contains ghosts. And sometimes you also would like to avoid that there are gradient instabilities. So this will correspond to the requirement that the speed of sound of this propagation of these fluctuations is positive or at least okay. So it's very easy to check that the previous the degrees of freedom of the previous action are actually stable, so do not satisfy these two conditions, by just using parameterizing the spatial metric in terms of a scalar degree of freedom in terms of this function theta, and in terms of the divergences part of the metric, which represents the tensor of degree of freedom of the metric. So once I do that, I plug this into the previous action, and then I simply write down the equations and I use some integration by part. I obtain this action. This is simply the harmonic oscillator action for a scalar degree of freedom and for the gravity waves. And the first requirement becomes, so for instance, if I want that gravity will not go like, I just require that the mass square is really the square of something real, and so that this is positive. And then if I want to do the same for scalar fluctuations, I require that these two parameters, so the alpha k plus 6 times alpha b squared, is positive. So you can write down stability conditions in terms of these fundamental parameters. And if I require no Lagrangian stabilities, well, this simply amounts to require that the speed of sound, which will be a function of all these alpha parameters, is positive or larger than 0, and then this is positive or larger than 0. So it's very easy to impose theoretical constraints on these parameters, even before comparing them to observations. So let us go to observations now. And in order to discuss observations, it is convenient to move from unitary gauge and to go to a gauge where things are more transparent for cosmology, let's say, or we are more used to it, if you want. And I will go to what is called Newtonian gauge, so the scalar perturbations symmetric are described by potential, phi and psi. And to do that, I just make a coordinate transformation of time. So I will introduce a scalar degree of freedom, which will be parameterized by phi, for example. It's not going to be done. Okay, usually when we have also heard this morning from David, when we want to parameterize the modifications of gravity, we go in the so-called quasi-static approximation, where you can neglect time derivatives of the metric and the scalar field. And this usually holds well below the sound horizon scale. Okay. So it depends a little bit on the sound speed of the cannon. And what one can do is to parameterize modifications of gravity in terms of this quantity, which one calls effectively to constant, okay, which usually is 1, but of course if you have dark energy, dark energy or modified gravity will be slightly different. And in terms of the sleep parameter, and roughly this enters in the way the growth of structure is modified, okay. And this will enter in the way light is value modified by the fact that you usually consider psi plus phi in the line and effect. Okay, what usually does is to write down these parameters in this approximation in this way. Okay, there are in fact there are theoretical motivations to consider this particular form that are valid that hold in this quasi-static approximation. Okay, so you parameterize these parameters in terms of phi functions as a function of time. It's the same number, but it's only a chance as the phi parameters that I included. Well, I think that it's time to go beyond this picture, okay, beyond the quasi-static approximation, but it's time to consider the fully dynamic regime, either by simply taking all the Einstein's equations that you derive from the previous action and write down the Boltzmann code, for instance, okay, just evolving everything like we do in general with GR. However, here, for the sake of arguments, I will give you two possible approaches that you can take to describe the modifications of gravity and dark energy. So the first one is a geometrical approach. What I can do is to combine Einstein's equations and remove the pi field, the fluctuations of the scalar field that I showed you before, from the equations, and write down an evolution equation for the curvature of psi, and the relation between phi and psi, where only matter and gravity are true. Okay. So this corresponds to have such a picture. So you modify the left-hand side of Einstein's equation. And this has been done by Mr. Wiki. And this is what you obtain. You obtain an evolution equation for the curvature, which is parameterized by a lot of these parameters, beta. Okay, it's a very complicated expression, but the idea is that this parameter all depends on five of these functions. So given these fundamental elements, you can go back and write down an evolution equation which is completely closed. Okay, you just need to add the evolution equation for the method, and then everything is given by these two equations. And here you have a relation between phi psi, and again there are parameters here that are a function of these alphas. A complete equivalent approach is to say, okay, suppose that I modify the right hand side of these equations. I describe now my dark energy of modified gravity as a fluid, as an effective fluid. There's not a particular physical, maybe there is not this fluid, but you can always write down the equations like that. And this fluid is characterized by an equation of state, which is very strange, very complicated, and it is this one. And again, all these parameters, gamma, that appears in this expression. So the equation of state is just a relation between the pressure perturbation and the density perturbation, the form momentum of dark energy, and the matter perturbation. And the same for the anisotropic stress. You can relate the anisotropic stress to the energy density, free momentum of dark energy, and matter perturbations. And then what you can do is make a sort of spectroscopy of dark energy, in the sense that each of these, by switching on and off each of these operators, you can change these two possible descriptions. So for instance, if I switch on alpha k and I switch off all the rest, I have simply a perfect fluid with a sound speed which is inversely proportional to alpha k, so I can go in the clustering regime for alpha k much larger than 1, for instance. Phi is equal to psi, which you expect for a perfect fluid because there is no anisotropic stress, and there is a simple relation between the pressure and the energy density. Now let me switch on, for instance, alpha d. So the kinetic energy of my scalar field is given by the mixing with the kinetic energy of the metric. So in this case, you don't have a perfect fluid because this relation is not the usual one, but still phi is equal to psi. Spiraling. You can switch on alpha m, for instance, and you will see that psi is different from phi. You will have effects in the propagation of gravity waves, and then again you can switch on instead alpha t, etc. Okay? You will have other effects. So each of these operators correspond to each of these operators correspond a very well-defined physical observation that you can try to track with your observation. And of course, I can always take the quadratic limit of these equations by getting rid of the time derivatives, and I will recover what I usually find in the limit of k going to infinity for the effective Newton constant and the steep path. Okay, so I think I can conclude. I hope that I have convinced you that this is the most general description of linear perturbations in scalar theories under some assumptions, and that provides you a systematic way to address stability and also to explore new theory. I think it's the most efficient way of looking at parameterize deviation from GR, okay, in this context. And there are a lot of things to do. Of course, one can generalize this approach by relaxing some of the assumptions that I made at the beginning. One can explore more the phenomenology or start making constraints, forecasts, etc. Okay, thanks.
Thank you very much. So, it's time now for question, comment?
Maybe it's stupid one, but still. Of course, I think you assume that at some level, this effective field theory which you have in some background cosmology would come from something covariant in 4 dimensions.
Sure.
But then I have seen you have several places where you have factors k to the 4, but you don't want time derivative.
Sorry, k to the 4?
K to the 4 factors in some places, which of course indicate that you have 4 spatial derivatives.
Sorry, no, there are no. Where?
For example,
Well, true that you have a, yeah, it's true. You have a key to the four terms here, so there is a strain to scale dependence here in this equation. However, when you look at the fundamental, for instance, you look at the equation, the evolution equation for theta, there were no higher derivatives, okay? And so in the, if you want, if you look at the propagating scalar degrees of freedom, you don't have a higher derivatives.
Also spatially.
Also spatial. Of course, you can generalize this. You can go beyond this.
If
but
you do be covariant, you cannot have more spatial derivatives.
I agree. Yes.
But,
I agree. No, it's true that here there are.
it totally looks like that. You say you could radically read
Yes.
the way that
In terms of theta.
Another question?
There's actually a very simple way of constructing consistent generalizations of gravity much beyond the Vernizzi class. You just start with a standard quintessence model, so matrix coupled to a scalar field, normal kinetic term, normal potential, so everything is fine. And then you take a field transformation, where phi is an arbitrary scalar function of the curvature scalar, whatever scalars you can construct, and the metric is an arbitrary tensor functions of, let's say a function of phi times r mu nu and e mu phi and so on and so forth. So whatever transformation you are doing, as long as it is invertible, gives you a fully consistent theory.
Yeah, as long as it conserves the number of degrees of freedom.
Yeah, that's
so
the
you have to check it.
invertibility. That's just the invertibility. But it's simple counting that it's much beyond the phi functions of Vernizzi theories. I mean, it's a huge class of theories that if you are considering only the tensor and scalar part are completely equivalent to standard quintessence. So the difference comes only that if you do your transformation, you have of course to do the transformation also in the matter part of your theories. This gives you different theories, but at least as long as it's just for constructing consistent theories, it's very easy, it's straightforward, and there's essentially...
yeah, my claim is that you will get the reaction that they should do that. And if you check the term,
Maybe you can continue discussing during coffee. Now we have to go to the next speaker, so let's speak ahead.
Thank you, organizer, for letting me talk on this topic. And actually, I was at Cape Town for several times to visit my old friend Raul Violier of his department. My talk will be basically on this topic, based on discrete symmetry. But we know that about 27% of the energy pi is CDM, and it is reviewed, recently I reviewed in 2 articles, and dark energy, it is also reviewed in new journals. And this morning I heard that actually Bacon commented there are 2 ethers. I agree with you on one. Certainly, dark energy is a kind of ether, but as you know, this cannot be the ether. It is not homogeneous over our horizon, in our horizon. Well, I took some pictures with famous inflationists, and I worked on with 2 groups on inflation-related work. One is the so-called K&B model, another is reading after inflation. Well, I base my talk on this very light action, which can work as CDM candidate if its age is greater than the age of the universe. It is based on Petrel symmetry. The detection of the action was suggested in 1983. in Korea, we established a big laboratory to detect action, and currently this ADMX is the largest laboratory in the world, but CAP really the bigger, much bigger than this ADMX. We know this WMAP cartoon. In this case, inflation occurred in this early age, and CDM and recent acceleration belong to this region. And probably I will try to explain all these things. Bosonic coherent motion. So I classify bosonic coherent motion in three cases. BCM1 is a kind of dark matter. This is a kind of inflation. Inflation is a kind of coherent motion of the bosons. And cosmological constant, temporary cosmological constant. Some people call this quintessence. So I start with axioms. I will succeed if I convince you that there is QCD action in the world. Well, because of instantaneous solutions of QCD, there exists an effective gluon-dual interaction. And certainly, this term is physical because we know that if the prime mass in QCD obtains QE1 much bigger than pion mass, it is solved by instantaneous physics. Therefore, instantaneous physics is physical, and because it is physical, there is a strong CP problem. Why is the neutral electric dipole moment so small? It is solved by the very light action, and this is the low interaction. Some strong interactions, strong interacting particles can generate effective contribution to neutron masses, and actually neutron dipole moment have a similar contribution attaching these photons. Many years ago, people calculated this effective coupling, but pion, being pseudoscalar, if it obtains vacuum expectation value, it contributes to this one. So this is the better estimate, and it is proportional to zeta bar. So there are two other solutions beyond very light action. There is light quark mass. U quark is massless. This is a kind of solution. As you know from this PDT book, it is not massless. And there's a symmetry principles. This is summarized recently by Nelson bar model. But this model has to give very small zeta bar, calculated zeta bar. So now only this very light action is considered to be the solution. Is oscillating in the action potential, and it is currently oscillating around the minimum of the potential. So this is the detection mechanism showing the previous cartoon. There is a strong magnetic field, and electric field follows the oscillation of vacuum action oscillation. Actually, this electric field follows the vacuum oscillation, and it contributes to E dot B interaction, electromagnetic interaction. So we try to detect this currently oscillating E dot B term. That is basically the detection method. So this is the previous one I showed you. That's the. Now I consider all these ideas are based on physical symmetries. If we consider theory allowed term, for example, string theory allows some discrete symmetries. If we consider only a few terms, leading terms, then we may have bigger symmetry, like global symmetry. So this part breaks this global symmetry, which was suggested by a few terms. So this was actually found from considering wormhole effect. If in our universe, or if wormholes take out gauge charges, I draw this flux line followed by these gauge charges, and if we try to see what happens to gauge symmetry, come of this wormhole, and it reflects flown out gauge charges. So we consider wormhole effects do not break gauge symmetries. However, if these flown out charges, global charges, there is no flux lines, therefore people consider this global symmetry is actually broken. And it was applied to Petro-Asian symmetry, and Petro-Asian symmetry is not good because always breaks global symmetries. That was summarized by some discrete K symmetries, many people, and therefore we can consider two solutions of this problem. From the effective field theory, from bottom-up approach, we can consider effective terms. But if we consider string construction, basically string construction contains, they claim it contains gravity. Therefore, we successfully generate all terms from string construction. There will not be any wormhole problem. So I take this point of view, and all global symmetries are not exact, including Petro-Asian symmetry. When we consider this kind of explicitly broken global symmetry, there are two terms. Vacuum expectation value of the global symmetry breaking term F, and also explicit breaking term, which I call lambda. Probably, if we consider global symmetry as a global anomaly coupling to gauge GG dual, this is the dominant term, probably numerically breaking this global symmetry. So I start with the dark energy from this principle. Well, for dark energy, if it is a vacuum energy located by the F of the dark energy global symmetry, then this must be very flat. This must be very flat. For action, it is not so flat. How can we have this one very flat and one not so flat? There are two global symmetry in this case. We can do this by this red term. Depending on the property of the red term, one can be the CDM, another can be the dark energy. This must be anomaly free because anomaly part is the very large part. So we consider this kind of potential. Generally, this height is when we consider grand string compactification. Next energy scale is grand unification scale. So if we consider this kind of global symmetry breaking is of this form. If it is dark energy, it must be very shallow. Well, I skip this one because there are some models where this can be realized. And basically, this is the philosophy. And if for dark energy, if the global symmetry defining term is a sufficiently higher order, this red part for this global symmetry can be very small. That is the idea. I try to interpret very small dark energy scale. This is the very small term giving this dark energy potential of this term, and this is dominant due to anomaly term. This is the QCD anomaly term, and so in this case, if we properly define this kind of a magnitude, the dark energy can be explained. When we consider this kind of potential, then maybe in the beginning of the universe started from hilltop. So this led to hilltop inflation. After bicep 2, we consider this one, the hilltop inflation can do something. Well, because if we consider very early universe, we may consider this is a small L region, and this is the one we try to explain. And for the hilltop inflation, I try to parameterize everything with cosine potential. Then actually it is impossible to explain bicep 2 data with hilltop inflation. Actually, freeze, Keynes, natural inflation data come here. All the hilltop inflation starting from top of the hill lies here. So it cannot explain this bicep 2 data. Actually, in the after bicep 2, chaotic inflation got lots of interest, but if you look at that in detail, it may not be so, because as you see, this is the hilltop, this is the chaotic inflation with quadratic potential, and this is the inflation point. MPC, it is very shallow, and there must be a fine-tuning on this case, because I base on my theory on discrete symmetry. So if I consider quadratic term, pi square term, why don't I consider pi to the 100th term, for example? Discrete symmetries always allow such terms. Then I have to fine-tune the coefficient very accurately to exclude all other terms. So that's the reason natural inflation was suggested by Chicago group. Natural inflation cut off all these large going terms by periodic potential, because strong interaction dynamics at the gas scale non-perturbably cut down all these high energy terms. But if I consider gas scale, this one is very small. This is not very small. If we consider this one, Light convinced us that the value of this phi must be very large, greater than 15 Planck. So that has the problem. And my friend suggested that maybe there are two actions. If there are two actions, one direction can be very large. And if there are two actions at the gas scale, there's no problem of this light problem. So we naturally consider inflation model in this bosonic coherent motion. And when we consider this one natural inflation with minus cosine potential, the K constant is actually obtained from this kind of Higgs-like potential. Then, to have this very large value, trans-Planck F, this coefficient lambda must be about 10 to the minus 6. If it is less than 10 to the minus 6, it is very small. So we must go back to hilltop inflation. It cannot be so. I showed that hilltop inflation doesn't work. So the radial direction. Must decay so fast. Radial direction. So radial direction is not inflation. So that's the reason we consider two inflations. Two inflation means two pseudo-scalars. We do not consider scalars in this case. This is the two pseudo-scalars. Now there is no scalars. And this is supposed to be inflation direction. I draw this another figure. There are two inflations. This direction is one inflation direction is not inflaton. This is inflaton. There are two. So one direction, the field rolls very quickly. Another direction, maybe very large. This is a very large F, the K constant. This happens in the following way. Basically, this can be inflation if I consider two actions, two minus cosine potentials. I consider mass terms of these two actions. This is the mass matrix. You can easily diagonalize this mass matrix. Then you notice that for this case, if alpha delta minus equal to gamma delta, it is exactly the same, and it is mass is zero. Therefore, if A is very near B, there is the case, if it is parameterized by delta, the near B, alpha delta is near beta gamma, then this mass is actually of this form. This lambda is cascade, and this defines the K constant, basically. So, very large K constant is actually possible. With this alpha, beta, gamma, delta are the quantum numbers on the Petro-Ecuador transformation. Alpha, beta, gamma, delta. And in fact, alpha, beta, gamma, delta is of order of 50 roughly. Therefore, it looks like there seems to be fine tuning. But so now I go back. I depart from this two inflation KNT model. I go back to hilltop inflation. What was the problem with hilltop? This is the hilltop potential. And actually, I need another field. So it is not drawn from this hilltop. I need another field to roll down. So it is actually, this is the previous hilltop potential. I need another field. At some point, it rolls down another direction. It is basically two field. In addition to hilltop radial direction, there is another field for the inflation. So this is the bicep 2 point. And I consider only this region. For the during inflation is taking place in this region. Therefore, there's no fine-tuning problem. It comes from some global symmetry. This potential comes from some global symmetry. Therefore, this is M got to the force. Therefore, in this region, there is no problem. So this is the attractive thing of global symmetry. So this was actually published some time ago, this year. And I can calculate some e-foiling number. This is not correct thing. I use some formula, but recently I scanned all the data points for these two field hilltop inflation, and the common region is actually behaving like this. I draw this figure again. Yeah. This. Sorry. I try to show this one. So I picked some point, E fold between. This is not that's the approximate formula. It is from the hilltop point. I run the evolution equation in the universe. So I calculated all the point and up to this bicep 2 point, and I obtained this one. There are few points that this will be plotted again. It will go up. And for specific parameter regions, this is E fold 50, this is E fold 60. So this is of this one. So it is different from other one field inflation for linear potential E fold 56 in this direction, but this is in this direction. This is in the two implant. Because this with this bicep 2 data, probably one of the nice things is that it restricts some saturated symmetric plating scale. And because in this case, we know that the Hubble parameter after inflation is about 10 to 14 GeV. What is the reading temperature after inflation? Actually, Bukumilla group calculate this one for neutrino. Right-handed neutrino field is doing leptogenesis, but it can be used for this case, but because probably the superpotential may be similar to this Bukumilla. In any case, it cannot be excluded. Actually, there's a flat region. This is the reading temperature. Even if we start from 10 to 12 GeV, reading temperature end up around 10 to 10 GeV. So if we use that, reading temperature after inflation maybe around 10 to 12 GeV. It is bigger than the current action window of the K constant. Therefore, if Petrarchan symmetry occurred after inflation, these two groups gave a very strong bound about action length. Marsh, Vicinelli Gondolo gave actually 71 microelectron volt. It is. It may not be accurate because these are based on the calculation of actions from the decay of system domain or string domain. They used this Japanese group data. It is about 50. But this can be different because there is a string domainal system. If string domainal system is like this one, for the case of n equal to 1, domainal number n equal to 1 case is like this one. If domainal number is n equal to 2, I can draw this surface. walls surfaces. So this kind of small-scale string wall system is not problematic. Only horizon-scale string wall domain, string domain system is problematic. So recently we commented that actually with n equal to 1, there is no horizon-scale string wall system problem. We will appear soon. And actually this is because if we accept related average mechanism, this horizon scale string wall system can be delayed by the collision of small scale domain. Now, because we have this problem of the action scale after bisect 2, I consider how we can obtain always n domain equal to 1. If it is n domain or equal to 2, there is no way we can erase this whole system as Skibby pointed out. We choose from string compactification a model with anomalous U1 gauge symmetry. Then there can be some intermediate scale Petrarchan symmetry. And also there is another way to obtain domain number 1 by rather Sharpie, but we do not use this one because this cannot be generally applied. We use some old method of some discrete groups of continuous Paul's conversion directions. So because this is very useful for string compactification, because string compactification leads to some global symmetry, U1 global symmetry from anomalous U1. If I consider domain number 2 directions, one domain number 2, one domain number 3, there are 6 distinct vacuoles. But this 6 distinct vacuoles can be identified by torus compactification of all convergent directions. And these 6 vacuoles are completely 1. Therefore, in this case, domain number is equal to 1. In this case, for this domain number equal to 1 case, recently I calculated this action photon-photon coupling. Action photon-photon coupling is of interest in action search experiment. Actually, people talk about in action search experiment KSVG DFSC models, but this comes also with many different models. KSVG always in the literature talk about only one quark carries some Petrarchan charge. That cannot be true. There can be many quarks carrying Petrarchan charges. And also DFSC model, there is no heavy quarks above TeV scale. That cannot be true. Therefore, it's better to calculate this action photon-photon coupling in a complete ultraviolet completed theory. So that I have done recently. Actually, this is a flipped SU5 model from string compactification. Here I know all the light field and all the quantum numbers in this case. So this is a technical details, but believe that I show that it is the correct quantum numbers because this is anomalous. There are 3 non-abelian groups. There is a flipped SU5, non-abelian group in flipped SU5. And this anomaly is -6984. This global symmetry anomaly. There's another flipped hidden sector SU5 prime. That is anomalies again the same number. There's another non-abelian group actually in the hidden sector. Actually, it is also the same. And there are lots of new ones. Not many, but some new ones. Therefore, I cite these things. And actually, these are the same thing. These U1s, I didn't properly normalize, so I didn't show. So for this non-abelian group, it is all same. All these entries of all these 6 U1s, this conspire to be the same number. So you can believe that this is the correct spectrum and correct anomalous U1. With this one, I calculated actually action photon-photon coupling. It is this number. And the I view KSVG line and DFSC line is here, and this green line is in between. This is just one order. Detection rate is actually square of this one. It is exactly between this KSVG line and DFSC line. So this is actually this one, green line. And recently, the related work in inflation was calculated by this Rothschild et al. And this, if this bosonic coherent motion is in this region, it is dark energy. If it is in this, it is CDA. So I try to convince you that there is a action. If there is a bosonic coherent motion, it can do many things. But global symmetry is not exact. Always it is broken. Discrete symmetry is the key. With the discrete symmetry, dark energy by bosonic coherent motion always should include QCD action. If it doesn't include QCD action, you can never explain dark energy because it has the QCD anomaly. The strong CP problem is solved, and the very light action provides some CDM component, and even a lighter one for dark energy. The one which is lighter than this QCD action can be a source for dark energy if the discrete symmetry is very chosen. I applied this idea of bosonic coherent motion to high-scale inflation with Omega number 1 models. It is possible in string compactification with anomalous U1, and in Korean CAP may get an answer to action in the micro to milli-electron volt range, even if this action is about 10% of CDM, 28% CDM. Well, experimentally, you cannot exclude this zero because the task study from Planck give about 0.2 is consistent with the one, but if I think they cannot determine the level of the contribution of 0.01. I mean, it is in the near future you cannot. Even if you have 0.01 at the level, the gravity wave from the beginning was at the 0.01. Still, energy density at inflation is of order of gravity density. It is about factor 10 smaller than the current number, but it is still gravity scale.
But it was just an optimistic thought.
But I think the bisector announcement is great in a sense that they draw the attention that actually this grand unification scale is the next level of the energy scale. And to exclude that, you need a lot of effort. And even if you can probably never exclude, because it is very difficult to measure R at the level 0.001 or even.
Maybe we can go for a coffee and continue because we are already late and we continue the discussion. That is,